So we're going to take a look at the difference between the initial value problems and the boundary value problems. In general, by the way, initial value problems are relatively easier compared to the boundary value problems. You'll understand in a moment what do I mean by that and why there is an issue with why there are issues with boundary value problems. So let me give you an example. An example of an initial value problem is something like this, right? So y double prime plus y equal to 0. That's a differential equation. And the initial values are, just going to say y of 0 is equal to 1 and y prime of 0 is equal to 0. So that means that what do you have here is you have a differential equation, right? And the only initial conditions, we only know what happens initially for that particular model that we are trying to model, right? That follows this differential equation, that follows this particular growth pattern in there. So if I know you all know how to solve this differential equation. So this basically says, it's a vibration problem, right? It's a vibration problem. And the vibration, it says the displacement is, 0. It starts at 1. It's the displacement, initial displacement is 1. And the velocity is 0, right? So the velocity is 0. And if you try to solve this problem, the solution to this problem is going to be, as you're going to see, it's going to be, I'll let you go home and solve this later. This is going to give you the solution of y is equal to cosine x. That'll be the solution to this one, right? It's no problem. Anyway, so going back to this initial value problem, so you have a solution. There's only one solution for this, right? Now let me give you a boundary value problem. So what is a boundary value problem, right? So let's take a look at this particular one. Same differential equation, y double prime plus y is equal to 0. And by the way, here we say the domain of the solution that we are looking for, or the differential equation, is x is positive, right? So it's in the entire positive real line. And for the boundary value problem, what you have is you have a condition. So the domain here is x is going to be between, let's just say, 0 to pi. So here x is going to be between 0 to pi. And the condition that is going to be, let me give you the condition. The condition here is y of 0, let's just say y of 0 is equal to 0, and y of pi is also equal to 0, right? So we are looking for a differential equation. We are looking for a solution that's a solution to this differential equation, and that satisfies this boundary condition. What do I mean by boundary condition? Here's my domain. Here is my domain. If you want, you can include this. Here is my domain. And so let me write it. Here's my 0. Here is my 0. And here is my pi. And the solution is supposed to start here and end there, right? The solution is supposed to start here and in there. It can go up and down, whatever it is, but I'm only interested in the solution between these two values, right? Solution has to start here and go back here. So solution can go like this, or solution can go like this. Solution can go various different ways. It can go like this, or it can go like that. Can go anything. It can do like this, and then it cannot do that. That doesn't look like a function. So it can go like this and then go like that, but then eventually it has to come down, or it can go down and then eventually it can go down and then come back up, right? So that's what the solution that we are looking for. So that's what we mean by boundary condition. The function must start at 0, and at pi it has to become 0, right? That's the kind of a solution that we are looking for. So if you look at this particular problem, what happens is the following. Let me ask you the following question. Would this be a solution? Can you verify this? Would this be a solution to this particular boundary value problem? Can someone verify this for me? So now this y2, this y2, is this a solution? No. Very good. Right? Now let me ask you the following question. y3, which is a 0, would that be a solution? So this is a solution, and this is not a solution. This is a solution. Now we are looking at whether this is a solution or not. And there are many other things that we know for the boundary value problems are no longer going to be applicable. All right. So the initial value problems are in some sense more predictable, nice, right? But the boundary value problems are not. Let me give you an example. So, for example, if someone is, someone is here at some point and throwing a ball, right? Here, throwing a ball with a velocity of throwing a ball in this direction, right? With a velocity of 10 miles per hour. Every time if the person is here, if the person is throwing a ball in this direction, the ball is going to go and then go land someplace, right? Every single time, correct? If someone is at this particular position, right, and then throwing a ball with some velocity, right, it's going to go land there every single time. So that's why you have a unique solution for an initial value problem, because the initial value problem gives you the, for example, in terms of applications, displacement and the velocity, you specify them, you're going to get it every single time. So that's why you have that unique solution. On the other hand, though, let me give you an example of a boundary value problem. The boundary value problems are like, you were like a guitar, you were like guitar, right? What happens in a guitar is you have two strings, you have a string that is attached to two different places, two different points, right? But you can make infinite number of sounds with that string, right? If you tap this harder, if you tap the string harder, right, you're going to have different sound. If you tap it lighter, you're going to have different sound. If you tap it here, you're going to have a different sound. If you tap it here, you're going to have a different sound. If you tap it here, you're going to have a different sound, right? So you have infinitely many sounds that you can create it out of a string, a single string attached to two different points, two different stationary points, right? Two different stationary points. So that's what the issue is, right? So so therefore boundary value problems have infinitely many solutions, and also so therefore they're harder to solve. It's hard to say if the solutions are unique if you have infinitely many solutions, or if you have no solutions, and so on. There are some there are some problems for those who want to. Here's the second project, again, extra credit. I'm not going to make it I'm not going to make it compulsory. So here is a problem, extra credit problem, those who want to do, which is solve this y double prime plus absolute value of y is equal to 0, right? And the initial condition is y of a, I'm going to say y of 0, let's make it that, y of 0 is equal to capital A, right? And y of b is equal to, let's just say 0, right? Now solve this problem for various a's and b's, right? Solve this problem for various a's and b's. Or I'll make your life even easy, right? Let's not even go there. Let's say y of 0 is equal to 0 and y of b is equal to 0. Now tell me how many solutions you're going to have when for various different b's. For example, if b is positive, or can you further divide the b into various parts, right? If b is equal to 0, how many solutions you're going to have? If b is between two numbers, right? How many solutions we have? If b is greater than certain number, right? How many solutions we have? So what I'm asking is, I'll again type it up and post it there. What I'm asking here is find the number of solutions for various different b's. For various different b's, find the number of solutions. This is a very, very interesting problem, and it's a boundary value problem, as you see here, right? All we know is that the b is a real number. B is a real number. Again, I understand this is a kind of a tricky problem. I understand that not all of them might be able to do it, but try it. See what you get. So in general, the boundary value problems are a little bit harder, or a mess, you may want to say. So if you want to see that how messy it is, try to solve this problem. You will understand the how the challenging part, or the fun part, or the messiness of the boundary value solutions of the boundary value problems. So I will stop it right here.